Hey pre-calc students, in this video we're going to talk about operations with trig functions and some basic identities. One thing, notation thing I do want to go ahead and get out of the way is talking about multiplying sine of x times itself. When you have sine of x times itself, there are a few ways that you can write this, and then there's a way you're not allowed to write this. So the first thing that's important to understand is that in order of operations, the angle is inside the trig. So x is some angle, and that is happening inside of a trig function. So a lot of times we put parentheses around the angle, but a lot of times we don't either because the angle is understood that it is happening inside the trig function. So if you're multiplying sine times itself, one way you can write this is sine of the angle squared. Another way you can write this is sine of the angle squared. And then the last most common way to write this is the sine is being squared and the angle is attached to the sine. So all of these are equivalent, where we'll see this the most common, where the sine is what's being squared and the angle is still happening inside the sine. One way you are not allowed to write this is sine of x squared like this, because it's not sure what this square is actually applying to. Is it applying to the angle? Is it applying to the trig? This is just not clear, so we never write it like this. Any of these options are acceptable. Okay, let's get into some examples and some identities. Okay, our first set of examples is some multiplying with some trig functions. So we'll cover some examples. In number 1, we have 3 sine of theta times 2 sine of theta minus cosine of theta. So I'm going to distribute my 3 sine of theta to both terms in my binomial expression. Whenever you're multiplying, you multiply your coefficients. So 3 sine of theta times 2 sine of theta is equivalent to 6 sine squared of theta. Again, I'm multiplying a sine times itself, so the sine is being squared. And then I have 3 sine of theta times or minus, so I'll bring my minus down. And then 3 sine of theta times a cosine of theta is going to be 3 sine of theta cosine of theta. Notice that I am keeping the 2 trig functions. I'm keeping the angle of the 2 trig functions. And I'm just writing them side by side because we know in math when 2 things are side by side that means to multiply. In number 2, where I have a cosine of theta minus 2 times a cosine of theta plus 5, I'm going to think about this as like the FOIL method or double distribution. First, I'm going to multiply my cosine of theta, then I'm going to multiply negative 2, and I'll look and see if I can combine like terms. See if you can do your distribution on your own. Okay, I multiplied cosine of theta times cosine of theta and got cosine squared. Cosine of theta times 5 is 5 cosine of theta. Negative 2 times cosine of theta is negative 2 cosine theta, and negative 2 times positive 5 is a negative 10. I do have some like terms here in the middle. I have 5 cosines of theta minus 2 cosines of theta, so these can combine. So I'm going to have cosine squared of theta plus 3 cosine of theta minus 10. All right, pause the video and see if you can try number 3 on your own. Okay, for this number 3, I distributed the sine of theta. So sine times sine is sine squared. Sine times tangent is sine of theta, tangent of theta. Then I distributed my negative tangent of theta and got minus tangent times sine minus tangent squared. Now in multiplication, order doesn't matter. So if I have a positive sine times tangent and a negative sine times tangent, these are still like terms, and I have one of each, a positive and a negative, so they do cancel each other out, leaving me with sine squared of theta minus tangent squared of theta. Okay, on this next slide, we're going to cover 3 examples of factoring. In the event where you have to factor anything involving trig, sometimes it's nice to compare it to a polynomial in that same format. So here in number 1, I have cosine squared of x minus cosine of x. So I can think about this. This would kind of be roughly the same concept of having like x squared minus x, right? Something squared minus itself. The reason why doing this is nice is because we're really good at factoring polynomials. I can see here that this expression has a GCF of x, and so I can take out the x, leaving me with an x minus 1 remaining. The same concept is true, but now instead of x, I have cosines of x. So to factor the original trig expression, I will need to take a cosine of x out of both terms. So if I take a cosine of x out of both of these terms, cosine times cosine would give me my cosine squared of x, and cosine times a -1 would give me a negative cosine of x. So here I have factored the original expression, and you can multiply, distribute back to check your work. See if you can try number 2 on your own. Okay, for number 2, saw cosine squared of x plus 8 cosine of x plus 7. So I compared it to the polynomial x squared plus 8x plus 7. And I knew I could factor this into x plus 7 and x plus 1. So I replaced my x's with cosines of x's, and I can also check my work. Cosine of x times cosine of x does give me cosine of x squared. Cosine times 1 and 7 times cosine would give me a 1 cosine plus a 7 cosine, leaving me with an 8 cosine of x for my like terms, and 7 times 1 would give me a 7. So this factoring works out. All right, take a look at my third example. Pause the video and see if you can factor number 3. Okay, so the first thing that I did is I turned it into a polynomial of the same form. I saw that I had a 2 times the variable all in common, so I factored out a GCF of 2x, which correlates to a 2 sine of x if I factor out a GCF of each of the original trig expression. And then my remaining quadratic was x squared plus 6x minus 3, which means I'm looking for multiples of -3 that add to 6. There are not any multiples, so this expression is prime, meaning it cannot be factored. So my final answer is 2 sine of x times sine of x squared plus 6 sine of x minus 3. Okay, another operation skill that I think would be beneficial for us to review is adding fractions when you don't have a common denominator. So the first example is 3/5 plus 1/2. In order to add fractions, we do have to create a common denominator. The easiest way to create a common denominator is to multiply your two denominators. So I can turn both of these fractions into fractions with a denominator of 10. If I want to turn 3/5 into a denominator with 10, I can multiply it by 2/2, which means I'm not changing the value of the fraction because I'm just multiplying it by 1. So 3/5 is the same thing as 6/10. And then to turn 1/2 into a fraction with a denominator of 10, I'm going to multiply both the numerator and denominator by 5. So 5/10 is equivalent to 1/2. Once you have common denominators to add fractions, you add your numerators. So 6/10 plus 5/10 is equivalent to 11/10. And we'll use this same concept for doing this with trig. So for instance, in this next example, I have 1 over cosine of x plus 1/5. I'm going to create my common denominator by multiplying my two denominators. So cosine of x times 5 is 5 cosine of x. So I'm going to turn both of these fractions into a fraction with that denominator. And then I also want to make sure I multiply my fraction so that my numerator changes as well. To get my first fraction to have 5 times the cosine. I'm going to multiply the denominator by 5 and the numerator by 5. So that will give me 5 over cosine of 5 cosine x. And then 1/5, I'm going to multiply both the top and the bottom by cosine of x. So my numerator of my second fraction is cosine of x. Once you have common denominators, we're going to add our numerators. And we're going to keep our denominator. Please be very careful. You cannot simplify this. We oftentimes cancel numerator and denominator when they have the same factor. But here in the numerator, I do have addition. So I cannot simply cross out the cosines because cosine is not a factor of the numerator. It is a combination of the numerator. So I have 5 plus cosine of x divided by 5 cosine of x. And again, the 5's cannot cancel and the cosines cannot cancel because I have this addition here, and so the 5 and the cosine are not factors in the numerator. All right, I want you to try the last example on your own. Before you get started, notice that sine of theta is not a fraction, and so to turn it into a fraction, you can put a 1 underneath it. Now you can create your common denominator and subtract your fractions. Again, pause this video and try it on your own. Okay, I created my common denominator by multiplying my denominators. I multiplied the first fraction by sine over sine. So I got sine squared of theta over sine of theta. And then I subtracted my fractions, subtracting my numerators, keeping my common denominator. Okay, before we continue on with some examples, I am going to call a recall of some identities that we have seen before in this class, and it's going to be really important that you know them. So the first group of identities are what are called the reciprocal identities. Reciprocal identities means you can do 1 over a trig function, and that is equal or equivalent to its reciprocal. So 1 over sine of theta is equivalent to cosecant of theta, and so forth. Again, we've seen these reciprocals before. And the quotient identities is saying that tangent of theta is equal to sine of theta over cosine of theta. Cotangent of theta is equal to cosine of theta over sine of theta. These are going to be really important, and you're going to want to have these memorized. Okay, the reason why you're going to want to have these memorized, especially reciprocal and quotient, is they're going to show up a lot of times in simplifying anytime you're dividing by fractions. So for instance, to review a fraction without trig, if I have 2/5 divided by 3/10, dividing a fraction is the same thing as multiplying by its reciprocal. So I can keep the first fraction, change division to multiplication, and flip the second fraction. And then you multiply your fractions straight across. So 2 times 10 is 20, 5 times 3 is 15. And the reason why it's important to know our identities is because they will show up when we have any simplification that can be done. For instance, 20 divided by 15 can simplify to the fraction 4/3. Okay, so let's take a look at the next example. I'm going to keep, change, and flip, multiplying by my reciprocal. So keeping 1 over sine of x, change division to multiplication, and flip cosine of x over 1. Multiply my fractions straight across. And here's where the use of an identity comes in. Cosine of x over sine of x is a quotient identity. And because of this quotient identity, I know I can replace cosine of x over sine of x with the trig expression cotangent of x. So my final simplified form is cotangent of x. Okay, for my next problem, if I want to be able to simplify the cosecant of theta divided by cotangent of theta, the first thing that I want to do is I want to turn them into identities where they will have like terms. So the first thing that I'm going to use is I'm going to use the fact that cosecant of theta is equivalent to 1 over sine of theta. This is a reciprocal identity. And I'm also going to use the fact that cotangent of theta is equivalent to cosine over sine of theta. And this is a quotient identity. Okay, so doing those substitutions, again, I'm going to replace my numerator cosecant with 1 over sine. And I'm going to replace my denominator with the cosine over sine. Again, the reason why I'm using the quotient identity here is all of these trig functions can be written in some form of combination of sine and cosine. And so normally those are the kind of the ones you want to look for. All right, see if you can multiply by your reciprocal and simplify this one from here. Okay, I kept my numerator 1 over sine of theta, changed division to multiplication, and flipped my denominator, so I got sine of theta over cosine of theta. Multiplied my fractions straight across. 1 times sine of theta is sine of theta. Sine of theta times cosine of theta is sine times cosine of theta. In my numerator and denominator, I have a factor of sine of theta, so they can reduce. Dividing a sine of theta out of both the numerator and denominator leaves me with 1 over cosine of theta, and I can use another identity. I can use the reciprocal identity to simplify 1 over cosine of theta to secant of theta. So my final answer here, the most simplified form, is secant of theta. Okay, for my next example, it says use identities to show that cosine of theta times tangent of theta times cosecant of theta is equal to 1. Whenever you're asked to show something using identities, you want to start with one side and you want to use identities, substitutions, and operations to see if you can get it to be equivalent to the other side. So the first thing that I'm going to do is I'm going to write down my left side of my equation. Okay, then I'm going to identify any substitution that can be done so that I can turn things into like terms. For instance, tangent of theta has an identity. I can use the quotient identity. And cosecant of theta, I'm going to use a reciprocal identity. And again, the reason why I'm using these two identities is because my goal is to turn everything into versions of sine and cosine so that I can combine as many like terms as possible. All right, so from here I can say that the expression cosine of theta times tangent of theta times cosecant of theta is equivalent to cosine of theta times tangent's identity. Tangent's identity is sine of theta over cosine of theta, times cosecant's identity, which is 1 over sine of theta. The next thing that I'm going to do is I'm going to try to multiply and simplify. I see that I have 3 fractions that are being multiplied, so I'm going to multiply my fractions straight across. So cosine of theta times sine of theta times 1 is cosine of theta times sine of theta in my numerator. My denominator is 1 times cosine times sine. So again, I have cosine of theta times sine of theta. And then I'm going to simplify and reduce. I see a numerator, cosine of theta times sine of theta, divided by itself, cosine of theta times sine of theta. So I know anything divided by itself will reduce to 1. Again, the goal was to show that this side equaled 1. And I did that. And I used identities to do that. Again, I'll do a little bit of color coding. I used the tangent quotient identity, and I used cosecant's reciprocal identity to do that. Okay, for my last example, I'm trying to show that 1 plus secant of theta, all divided by tangent of theta, is equivalent to cotangent of theta plus cosecant of theta. So again, I'm going to start on one side, and I'm going to use simplification techniques, algebra techniques, and identities until it looks like the right side of my equation. So the first thing I'm going to do is just rewrite my left side. Okay, and I'm going to kind of check in with my answer and try to figure out where I'm trying to go. I noticed that I have one fraction here, and I'm trying to show the addition of two fractions. Again, I know that cotangent can be written as a fraction of cosine over sine, and I know that cosecant can be written as 1 over sine. So these are two fractions separated by addition, and here I have one fraction. So the first thing that I'm going to do is I'm going to think about, and I'm going to undo the addition of common denominators. So I have 1 plus secant of theta, and all of that is being divided by tangent of theta. This is equivalent to having 1 divided by tangent of theta plus secant of theta divided by tangent of theta. And again, this is true because if I wanted to think and go backwards, these two fractions have common denominators, so I could add the numerators and keep the common denominator. So these are equivalent. You can also think about this as dividing by both terms by tangent. And now I want to see if there's any identities I can use. Well, the first identity that I notice is the 1 over tangent of theta. 1 over tangent of theta is equivalent to cotangent of theta. This is a reciprocal identity. The reason why I'm going to use that identity is because I want a cotangent of theta in my final answer. So I'm going to go ahead and substitute that in. And again, all I've done is replace that 1 over tangent of theta with cotangent of theta. Okay, so I have that part of the identity. Now the other goal is trying to turn this fraction, secant of theta divided by tangent of theta, into cosecant of theta. Well, I don't necessarily see an easy identity that I can use to immediately do that. So I'm going to try to turn secant and tangent into like terms. I know secant can be turned into 1 over cosine, and I know that tangent can be turned into sine over cosine, so that I have some like terms there that I can simplify and work with. So I can use a reciprocal identity and a quotient identity. Okay, so I need a little bit more space here. Okay, so I'm going to keep my cotangent, right? I'm using equal sign, so I'm saying that all of this is equal. So I'm going to keep my cotangent of theta. And I'm going to replace my secant of theta and tangent of theta with their respective identities. Okay, now I see some simplification and multiplication that I can do to simplify this fraction. So I am going to finish this problem off, see if you can finish it. You're going to need to do a keep, change, flip here and simplify this expression. So pause the video and give the remainder of this problem a try. Okay, walking through my steps a little bit, I did keep, change, flip. So cotangent plus 1 over cosine times cosine over sine. I multiplied these two fractions, so that left me with cotangent plus cosine over cosine times sine. I saw the common factor in this fraction, so I simplified to cosine of theta plus 1 over sine of theta. And then 1 over sine of theta is a reciprocal identity, can be replaced with cosecant of theta. So I replaced 1 over sine of theta with cosecant of theta. So that, again, that was leaving me with cotangent of theta plus cosecant of theta. Notice that the cotangent kind of traveled along with this process because I'm saying all of this is equivalent, equivalent, equivalent. So notation says I need to make sure I'm preserving all equivalent aspects. So the cotangent kind of from the beginning has been kind of simplified there. We had it. We were just trying to show that the cosecant of theta was also there as well. Okay, that's it for this video. We'll try more with this in class tomorrow.